All right, folks, so let's talk about energy in terms of what we call thermodynamics. So you should have your notes packet ready, and what you want to do is fill in the notes as we go through these slides. So what we are talking about here is energy. So when we think about energy, we think about heat, we think about the direction that heat flows, and then we think about units of heat. We're going to use two units. Calories you're familiar with. If you think about food, if something has 500 calories, you know what that means. The other unit that we're going to use is referred to as joules. No, not those joules. Joules as in the unit for energy production. So let's go through and look at some of the terms. So if you look at your first page of your notes, there's a paragraph there. And it says orange growing is an important industry in Florida's economy. If an orange grove is below freezing for just a few hours, it can have devastating effects to the whole crop. In other words, your oranges will freeze. One technique for preventing oranges and trees from being severely damaged is to spray them with water before they freeze. If we sprayed you with water before temperatures went below freezing, you would get frostbite and possibly die from hypothermia. So why does spraying a tree with water potentially protect it from freezing? That's a question you're going to want to answer when we're done with this unit, so kind of keep that in the back of your head. All right, let's define some terms. So when we say thermochemistry, what we mean is the study of energy changes and the direction of heat flow. So in other words, what we're going to say is, let's say you have a beaker of something, let's say it's water, and you put something in that beaker and it starts to heat up. So what we're going to say is, what's the direction of heat flow? If heat is flowing out of the system or into the system, those are some things that we're going to look at over the next couple of days. Okay, so the next thing we want to talk about is chemical potential energy. Let's say you're looking at a chemical. Let's just say, for example, it's water. The water has this structure. You've got a hydrogen bonded with an oxygen, another hydrogen bonded with an oxygen. So chemical potential energy is the energy stored in chemical bonds. So what we want to figure out is how to release that energy. So that's the whole idea. Take some things, mix them together. Does it release energy or does it require energy? So it says type of substance will determine how much energy is stored in bonds. So for example, if you have gasoline, you're basically paying for the stored energy that can be transferred from when you move from one place to another. So in other words, gasoline contains a lot of potential energy. You put it in your car, you convert it to heat, and your car moves. So why study thermochemistry? Very simple. Where we get our energy from. So in terms of gasoline, oil, electricity, basically any type of heating or fuel deals with what we call thermodynamics. All right, move on. So let's define a couple of things here. So we're going to say that heat is sorry about that. Get a pen. So heat is the transfer of energy. The symbol that we use for heat, Q, and the unit for Q is joules or capital J. So whenever we say solve for heat or calculate how much heat, that is what we are talking about. We're solving for Q. Heat flow, then, what we're going to say is energy always flows from hot to cold. In other words, if you put a hot cup of coffee on the table, say it's 100, or let's say it's 99 degrees Celsius, what's going to happen is that coffee is going to transfer heat to the air and it's going to cool down. You're never going to transfer to something hotter and heat it up more. always from hot to cold. So kinetic, I'm sorry, chemical kinetic energy, what that is the motion of molecules. So as molecules move, and specifically as they move faster, it produces more heat or what we would say more energy. So if something has more energy, it has a higher temperature or more heat. So anyway, let's move on. So when we talk about heat flow, we mentioned this a little bit earlier. What we're always looking at is the system and the surroundings. So for us, the system is usually going to take place in some sort of beaker or container. So for example, what we're going to say is some sort of reaction taking place in a beaker. The actual system is the actual reaction itself, and everything else is considered the surroundings. So the air here, your skin, anything that comes into contact with the chemical reaction. So the actual beaker is part of the surroundings, surrounding what's going on inside of it. You just want to be aware of that. Sometimes people think the beaker and everything is it. I'm sorry. People think that the beaker and everything in it is the system, actually the stuff inside the beaker. All right, so the way we can calculate this by using what we call law of conservation of energy. What that is, it states that energy cannot be created or destroyed, can only be transferred from one system to another. In other words, rid you can't get rid of energy. The only thing that you can do is transfer it. All right, let's talk about heat flow now. We're going to describe two terms here. Endothermic and, oops, let me get a pen. Endothermic and exothermic. So the two prefixes, endo and exo, basically mean inside and outside. So if something is endothermic, what we say is that it absorbs energy. The energy goes from the surroundings to the system. If something is exothermic, we say that it releases energy. So in that case, goes energy transfer from the system to the surroundings. So the first thing we need to do is figure out, are we talking about a physical process like water warming up or cooling down for that matter? Or are we talking about a chemical reaction? And we'll look at this in much more detail as we move forward. Basically what happens is if you have a chemical reaction and it is exothermic, it's releasing heat and it will feel warm. Let's say it'll get hotter or warmer. If it's endothermic, it's absorbing heat and then it's feeling cooler. If it's a physical process and something is warming up, that means it's endothermic, so it's absorbing energy and getting warmer. If it's exothermic, it's releasing its energy and it's getting cooler. So whenever you're looking at a process, the first thing you got to do is determine, are we talking about a physical process or a chemical process? All right, let's take a look at some examples. Let me get a pen here. So let's say your hand gets cold when you touch ice. So again, is that a physical process or a chemical reaction? Well, clearly that's a physical process. So if your hand is getting cold, your hand is releasing heat, so it's exothermic. Your hand is getting colder. The ice, on the other hand, it's endothermic. It's it's absorbing that energy. So let's say ice gets warmer when you touch it. So now what we're looking at is the ice. We just said the ice, according to the ice, is endothermic, getting warmer. Let's talk about water boiling on a kettle. Again, that's a physical process, not a chemical reaction. If the water is getting warmer, it's absorbing heat, so it's endothermic. If water vapor condenses, so if something condenses, it goes from a gas to a liquid, which means it's cooling down. So that means it is exothermic. And then if you look at ice cream melting again, ice cream melting is another physical process. It's getting warmer, so it's absorbing heat, so that is endothermic. All right, so what we're going to do is take some time and you're going to work on the things in your practice packet, and then you are going to do the practice quiz when you are done. Let me know if you have any questions, and that is all, folks.